We now start to discuss the design of routers themselves, the specific elements that's inside these things that we simply draw a little box when we're connecting network nodes. So then let's think about what a router needs to do. It really is relaying a packet from one channel to another, in fact to another channel downstream. So you have to decide what that downstream node should be, and in other words, which channel to go out of. And this is what you may call route computation. You need to know where to go. Once you decide to go out, let's say, of your east-going channel, in fact, you need to figure out which virtual channel inside that channel to use. So for instance, the topology would determine my upstream neighbor, this node over here, is connected to one downstream neighbor, one neighbor in this particular way. So the packet that comes in that wants to go there, if it came in from this channel and it wants to go there, the route computation may decide to use this outgoing channel. Okay, that's route computation. And since virtual channels are used all the time, in fact, within this one physical channel that comes in, there may be a number of virtual channels within that channel. So what you're really deciding at this node is which virtual channel of the downstream neighbor that you need. So that's part of the calculation. You also need buffers. You need to put the packets in the buffers if there is no downstream, if there is no channel bandwidth for you to allocate during congestions, for instance. But the canonical design, in fact, the packet comes in, what they did is they go right into the buffers. And only when we find out available bandwidth do we take them out of the buffer and forward them to the next stage. And finally, once you drive the signal from a channel, it will be received by the next router. So there's all these things that can be done. It's canonically broken down into 4 stages. This is very much like your 5-stage risk pipeline. It's a conceptual thing. It doesn't have to be these steps. You can have many more stages in your pipeline, as we will see one example later on. And you can also play tricks to get rid of some of the dependencies and try to make the whole computation, the whole process go much faster, and we will see that as well. So all of this following discussion is based on this canonical, sort of one typical way of building a router, and it involves computing the route computation, virtual channel allocation, switch allocation, and switch traversal. Okay. So packet comes into a channel, and then you decide to compute the channel, the route, and therefore picking what physical channel. And then the next step is to pick virtual channel. Then you cross the switch when you get the chance, and this requires allocation. We have to globally look at the demand of all these channels and decide who wants to go where, what is the best way to use this switch, go across it, and keep on driving. And finally, that's only router delay. So this is router delay, the TR that we used to have. So if you have H hop, then the router delay is H times the TR. And then you have to traverse the channel, and this is largely determined by the propagation delay of the signal. And this may be asynchronous. It may not be an even number of cycles in terms of the router computation. It could also be synchronous. So let's look at this in a very specific example. Here's a little bit of a cartoon showing you the specific components, okay, assuming a 4 canonical stage pipeline. So there would be I guess this is recursively defined. We call this whole box the router, and then there is a component to carry out the function of route calculation. This could be a routing table, this could be some logic. As you recall, that we have algorithmic routing algorithms. So this route computation is unfortunately, at least in this textbook, called a router again. So this is, if you wish, you can call it routing table, which kind of implies that it's a table-based routing algorithm. That's not necessarily the only way to do things. So anyway, you have the route computation, and then you have the buffers, okay, for each virtual channel within a single physical channel, okay, and you have metadata to keep track of what they want. So for each channel, this is what you have. You have buffer space for flits, maybe for packets as the unit, it depends. And then you have all kinds of state, global state, what the route you computed, what the output virtual channel you decide to use, and so on and so forth. Credit, we'll get into that detail. So you have this for every virtual channel, and then for the entire channel, you may have a lot of these, okay? And the information is being retrieved or sent to the VC allocator, which, based on all the information, would pick a virtual channel. And once you decide what that virtual channel is, you go to the switch allocator. And this is really every channel's information is centralized to the switch allocator, which decide who's going to use the switch this cycle so that the data comes out to the output unit. The output unit is effectively connected to the input port. So this is the same thing as downstream this component over here, right? So the information that gets replicated a little bit is credit and global state, stuff like that. But for the most case, we don't need a buffer. We'll talk about that. But most of the buffer is really just a driver. So the information comes in here, and then they get driven onto the on the wire, so that they are arriving at the next router and going into a specific set of buffers. Okay. Now let's look at a little bit of cartoon, and let's say I have a packet. The header is shown here in blue, and then some body flits that comes in. This is already traveling on the wire, so we're looking at this node. Let's say in one cycle it arrives, and therefore it will be buffered into, here's the buffer over here, and this is some of the relevant state that we're gonna look. And here, this is really just a way of showing the timing of it. So let's say first cycle we got the header flip, so we're ready to process this. So in this cycle we process it. At the end of the cycle we may decide, okay, we're gonna go out of the east channel, going there. So then we will say we're in a routed state. Then we have to allocate which virtual channel. Pretend we have two VCs, VC1 and VC2, and they're associated with two sets of buffers. Okay, so you have to decide which one you want to choose. Not the least of which you need to know is which channel has capacity for you. And let's say we decide it's VC2. That's the virtual channel that we're going to use. So at the end of this cycle, we have that piece of information figured out, and the next cycle we decide to do switch allocation. Now, meanwhile, the packet, the rest of the packet flits are still coming in. Every cycle or every fixed amount of time, a flit arrives. And then once we decide the switch allocation is done, we say, okay, based on the allocation, this packet over here that we're talking about gets to transfer. So then after that cycle, on the switch traversal cycle, we will go through the switch and gets latched at the output VC2. So this buffer over here is just one entry. It's really not a buffer for keeping the data, but to drive the signal. And so this cycle completes. Next cycle, it will go through channel traversal, and in the end arrives at VC2, and the whole process we just described repeats all over again. Okay, so if you look at this, and this continues for the rest of the packet. So if you look at this, this is really perhaps three different components, somewhat disjoint. The switch, which is a centralized thing, and the input part and the output part. Okay, there are these three different components. They are somewhat disjoint. Each one is working, especially the input and output port. They're all working in their corresponding channels. There are multiple independent units. The only thing that ties everything together is the switch allocator, because this is only one switch, or crossbar, if you wish. Again, crossbar is not necessarily the only thing that you use, but it's usually implemented as a real crossbar. So multiple channels are connected to the switch, and they're all then connected to the output units. That's about it. You have all these things. You have the relevant metadata. Global state would tell you whether the packet has been routed or not. Is it waiting for virtual channel? So you have your finite state machine. If you computed the route, this has to be recorded. It's part of the metadata. You will need to know what is the output or input virtual channel. So here on the input side, the output virtual channel tells you what was the virtual channel from the previous node. Then you have pointers, because you have buffers collecting all these flits. You need to know where's the beginning of your packet, where's the end of it, and you have credit. So you know what the current credit is. You know what your downstream virtual channels credit is. So it's everywhere, metadata. And this is just, again, one example of, we can design things this way. It's not the only way of doing things. So we'll see one example perhaps, and that is also just one way of doing things. And this is a case study of an alpha processor, which was one of the earlier processors that decided that the integration roadmap is going to be we integrate more processors into one chip, and each one will be associated with a router. And this is their diagram of how they do it. And the chip is called 21264. The core itself is really not very different from the earlier processor called 21264, which we kind of visited when we were talking about the shared memory substrate, the LSQ. Alpha is one of kind of my favorite processor, not in the sense of it's well designed, but it's really well documented, and you can read about what they did. It's next to IBM, which documented even more. This is my favorite. They have so much information. Unfortunately, the processor was no longer produced. The company went out of business. It was bought up. So anyway, the pipeline stage is very different from what we imagined. Okay? It's a 9-stage, 9 logical state. Yes, there is the routing. It's not called RC, but who cares? It's just a name. Very interestingly, this happens a lot in high-speed microprocessors. They're explicit stages just for the transport of things, wire delay. Okay, and then the route computate what we call virtual channel allocation was sort of distributed function into a lot of different stages. So here's decode and write table entry. What that means is data comes in from the channel. Okay, we need to compute where to go and then decide which virtual channel, then we write it in. We write the entry and metadata into the data structure, put it in there, and then we go through the switch allocation. The switch allocation is in fact calculated in 3 individual steps. You first decide locally which packet you want to send. So instead of everything comes together in this global arbitration, it's done locally. You pick, and then you have to read the data out, drive them to the output unit, okay, to be ready. And that's another stage. And then there's the global arbitration to decide, okay, this one we're gonna pick, that one we're gonna delay or whatever. So that's one last stage. And when the crossbar is done, it takes another cycle to be written into the output unit before driving on to the channels themselves. And in fact, one of the stages that we didn't even mention at the very end, there is ECC to check if something is wrong. So the pipeline works roughly like this. Okay, for the first flit, you need to do all this stuff of route computation and basically virtual channel allocation. For the subsequent flits, you don't have to do that. Now, even for the first flit, sometimes you have different types of packet, so the pipeline, in fact, is it depends. It's not just one stage. Sometimes it goes through 2 different ways of processing the first flit. The network came with 3 VCs, 2 VC0, 2 adaptive VCs, and 1 special VC. We talked about this before, how this network avoids deadlock. One of the way that the deadlock was avoided was by using an escape route. So it's an interesting router in that even though we only think about this, actually the chip was designed to be a planetary 2-dimensional chip, perhaps cut into these little tiles. So you have a core and a router for every node. So you have, and it's a mesh connection. No, sorry, it's a torus connection. It actually has the wraparound at the end of the dimension. So you have 4 next door neighbors. But the input port is actually fairly complicated. You have the local input port, that's the processor. You have a port that allows you to go to the I/O, memory controller, and so on. So you have more than 1 local input ports. And so all of them added together, it ends up being a chip, a router that supports 8 input ports and 7 output ports. Of course, you don't have to use all of them. It's a cut-through routing. So if you still remember, the difference between cut-through and wormhole is how memory space is allocated. If it's by packet, it's cut-through. If it's by flit, it's wormhole. So it's cut-through routing here. The packet, the buffer is sufficient for the whole packet to arrive. You don't have to worry about that. So a packet will not be stopped midway due to lack of receiving flit buffers at the end. Okay. This is very complicated, kind of different ways. So we talked about different ways of different types of deadlock and perhaps different ways of handling some deadlocks. This processor used a lot of them. from fetch deadlock, there are 9 different classes of messages. So we can think about them as virtual networks. Remember, if I have a response network, then that network will never be clogged. It will always be drained by the user, because that doesn't require a response on top of that, on top of a response that you get. So there are 9 classes. No, some of them are not for fetch deadlock per se. For instance, if you want an I/O packet, a read from a different node in I/O, then you have to use a separate class, because I/O packets are somehow ordered in a totally different way, and you have to guarantee that there's no bypassing. So that's details that's kind of not relevant to the general discussion of how the major principles of building routers. They have adaptive minimum quadrant routing. Okay, still remember that? We do minimum routing. Okay, so we don't allow you to misroute, but it is adaptive. Okay, so it's not therefore deadlock free. It's not dimension order routing, so it's not guaranteed to be deadlock free. The bulk of the buffers are associated with the adaptive VC, meaning VC 0 and 1, they're adaptive. This is the common case. We let things go, we hope things are fine. Most of the buffers are associated with it, so we can do whatever we want, but boom, what if I have deadlock? Then I use escape VCs. Okay, one on each dimension. There is one escape VC for the horizontal dimension, one for the vertical dimension. So how do you do that? Well, in even one dimension, now we have, if it's a mesh, you don't have a deadlock possible, because it's not even connected. You have 4 nodes, they're connected. So for instance, in going this way, the node arrives, the message arrives at that node, then will definitely be withdrawn from the network. You don't have to worry about it. But since we have a torus, then we can have A is waiting for B, which is waiting for C, which is waiting for D, which comes back and wait for A. And they use 2 escape VCs. This is how they choose to do that. This is an example of 4 nodes on one dimension. Okay, you see processor 0 being repeated. So this is just unrolling the whole loop. And depending on where you want to go, the VCs are allocated this way. You see, there's the dashed ones, and then there's the solid one. So in any of these connections, you don't have a full wraparound of dependencies. So if you're in processor 0 and you want to go to 3, then you use these VCs. Okay? If you are a processor 2 and you want to go to, if you are processor 0, you want to go to processor 2, you can't go to 3. Go to 3, you go on the opposite direction. If you want to go to 2, you use this channel. You want to go to from 1 to 3, you use this channel. Okay? And there is no dependency, no circular dependency. 3, for instance, depends on nobody. It's waiting for nobody. Now on the other channel, on the other virtual channel, I should say, it's the remaining routes in this one dimension. So if I have a one-dimensional system and I allocate my route this way, the 2 VCs, you can kind of think about them as the height that we were talking about. This is your ground floor, this is your floor 1, and it's not quite the same thing, but that's the idea. You're being allocated different VCs, and those VCs themselves don't have the possibility of forming a dependence loop, so you're deadlock free in that dimension. Okay, So in a single dimension, this is always what happens. And when you have interdimension, so I'm going in one dimension and I'm turning onto another dimension, they only allow you to go on to the adaptive VC. So you go on this unless you are unless you arrive at the current row, okay? And because, remember, it's minimum adaptive routing. So if I arrive at the row or the column, suppose that's my last dimension, I arrived at the column of my destination and I'm using minimum adaptive routing. What does that mean? I cannot go out of this row. I have to keep on going, and this guarantees that I will not be deadlocked. Okay, so you can use the escape VC if you arrive at the destination row. So that's how they avoid network deadlock. And now we come back to more general discussion about routers. This is no longer 21 to 364 specific design. So let's think about credit flow just a little bit. Now I'm showing you the timing of some packets, from some flits. This is the head flit and body flit and so on and so forth. And the color indicates excuse me, two different nodes, the upstream node in white and the downstream node in shaded color. Okay, and W means wire delay, and we're assuming a wire delay of 2 cycles, and in this case 5 body flits plus the head. So let's look at this, right? So we have 4 flits, 4 credits at the beginning of this this train of flits, and we're sending one downstream, which we know would result in having only 3 available buffers. Okay, so cycle 1, meaning the light colored upstream neighbor, successfully allocated the channel, allocated the switch, and then therefore crossing the switch at the next cycle, 2 cycles later, arriving at the destination, at the downstream destination. And at cycle 5, this head flit allowed the downstream node to start route computation. And it would go through switch allocation at cycle 7. Okay? So when that happens, when cycle 7, the switch allocation succeeded in the downstream neighbor, then at the end of that cycle, this is where we're talking about, we can generate a credit packet backwards to the light colored node. Okay? Because we know this flit has left this station, therefore we have one more credit available for your consumption. So let's see, because we had 4 flits or 4 credits at the beginning of this whole thing, and every cycle, let's say we successfully allocated a switch and transmitted the entire the entire flit and keep on going. At the end of cycle 4, and this is here, we run out of our credit. We know that this body flit 3 is the last flit that we have guaranteed the storage downstream, and at cycle 5 we will not even try to do switch allocation for body flit 4 because we know we run out of credit. We shouldn't even try. So meanwhile, the other side of the story, the credit was generated, assuming 1 cycle. Again, these are all examples. This could have been done in no time at all, hidden in the wire delay, whatever. But assuming it takes a cycle, then it will take 4 cycles to be updated back at the upstage, the upstream neighbor. Okay, it takes the same amount of time to go backwards on the wire, takes a cycle again to upgrade. So at the end of 11 cycle, so cycle 12, we know we have 1 credit. That's why at that cycle we allow body fleet 4 to be switch allocated and potentially winning the switch, and we go. And this is an ongoing thing. You can see that as these body fleets also leave the downstream neighbor, they will create corresponding. This is corresponding to body fleet, to head fleet. This is corresponding to body fleet 1, and so on and so forth. Okay, so a credit takes this amount of time to get there. Okay, it's the entire fleet. That's over here. That's this whole delay. We start from a clean slate. The fleet delay, it's kind of, it's over here. We have the 4 stages plus 1 wire delay, and that's over here, plus 1 cycle. That will bring us to the processing of 1 fleet, 1 credit going backwards, and then that takes the credit update or processing cycle. That's this plus going backward 1 wire delay. So you see from this, from the sending of the first fleet to I can send another fleet, this is the minimum I need. If I have a packet or a fleet that I'm sending downward, it will take this long for that packet. In the best case scenario, it could arrive at the next store at the downstream neighbor and not be able to further propagate. So I won't even get a credit. But the minimum amount of time is this many cycles. In our example, that would be, I guess that's 4, that's 2, this is 2 times 2, 4 plus 1, that's 11 cycles. Okay, so starting at cycle 1, I sent something. The best I can expect is at cycle 12, I get a credit update. So in this case, I only have 4. If I had 11 credits, I could do this without interrupting, without stopping for credit. But in this example, we only have 4 credits, which is why we have to stall for here 7 cycles. Okay, we didn't have any credit left, so we cannot proceed. So that's how credit flows. Again, we talked about this. This is again an example, but actually it's not quite that easy. When do we send the next packet? There is, you can call that the channel reallocation issue. What if I run what if I finished all my flits in the previous packet? When can I send the next independent packet? Okay, should I do it now or when it gets empty? This is actually the issue. So let's first see the problem. Showing a little bit of a cartoon with these directions. Okay, so the left hand side incoming channel, and then the right hand side I'm going, these are incoming channel to this node, and this is the outgoing channel. I'm not drawing all the channels. Okay, so basically, oops, the oh, let me go back. The animation, the cartoon here shows that I'm not drawing this for simplicity. So let's say that we decide to send the red channel, the red packet first. So the green packet got buffered. Okay, so the red packet used virtual channel, let's just call that VC3, and then it's gone. Now, is VC free for the green packet? Okay, if you want to use the resource there, the buffering resource, you can say, okay, I can send it over, right? Because red channel is done. But now imagine if the red packet, for some reason, the last flit cannot traverse, got blocked. Now your green, even though it wants to go somewhere else, it has nothing to do with the red, can get stuck behind the red packet. So this is a problem that you need to consider. It's not a problem as in there is no solution. This is something you need to worry about. There are lots of solutions to that. You can say, okay, first let's not allocate the channel unless it's empty. Let's not allocate this VC unless it's completely empty. With many virtual channels, pick another one. It's one solution. Or you can say, let's make the virtual channels more complicated, that it allows out of order processing, that I can have the red sitting there, but I'm yanking the green one to do a channel traversal to a completely independent channel. You can do that. Just you have to balance which one is worth it. You have to see how often this happens and whether it's worth it to do the particular design that you decided. Okay, and the consequence of that, just to drill on this particular problem a little bit. So the conservative approach was to allocate the VC to a new packet only when it's empty. Okay, so in the example that we're showing, it's sort of, this is the red packet over here, the head flit and tail flit. Okay, and this is the head flit of the next packet. Okay? The conservative approach would be to say, no, I'm holding on, even though we may have credit, we're not doing anything until here. Where is here? This is when the tail flit has arrived at the destination. It didn't have to go through RC or VA, but we just put in there to tell you the timing. So once it successfully accomplished the switch allocation, we know that it's going, therefore we generated the next cycle, the credit update, and this credit update arrives at the upstream neighbor here. That's when we know, since that's the last flit, that's when we know the credit has been restored to the maximum. That's when we send. Okay, so B is a little bit more aggressive. It says, okay, who knows? Maybe the tail flit will not be blocked, so this is faster. Kind of driving like on the highway, if you see empty space, do you know that it's faster? You don't. So speculatively, you can say we send the second packet, we compute it there, and then we already send the packet over, and therefore it arrives before the flit left, the tail flit left the downstream neighbor. We could get stuck, or we may not get stuck. So there's a little difference between B and C. I'll leave it to you to read for the detail, but here is sort of one example of what you need to consider when you're building these routers. There is no one way of doing it. There are all kinds of problems you need to consider, perhaps simulate their performance. Now, let's talk about some of the ways to make things go faster. We have these 4 canonical steps. Do they have to go in sequence? Not necessarily. Here's one way of speculatively doing 2 steps at the same time. Virtual channel allocation depends on route compute. If you don't know which channel you're going, you can't allocate the virtual channels in that physical channel. You can't do switch allocation until you know which output channel you want to go to. So these 2 all depend on RC, but they're not necessarily all depend, SA does not necessarily depend on VA, okay? It does in the sense that otherwise you're allocating prematurely, and that can be a waste of resource. Okay, so if you allocated switch before you even know you end up having a VC to get into at the destination, then you could get the switch resource and not use it. Okay. But if latency is what you care about, you can do these two things at the same time. And so, of course, two things doing at the same time, we don't know if they will be successful. What I failed to mention is that when you have these channels, let's say you have VAA, okay, and that didn't happen. Like we run out of available virtual channels, and then just like your regular pipeline, you will introduce bubbles after this stage. Okay. So, if your virtual channel failed, then you try next cycle. You just delay the whole thing. Okay. And the next cycle, you again do VA and SA at the same time. Again, you can run the risk of getting SA, the switch allocation, completed, and you have nothing to send. This happens. This is like any reservation system. You think you're going to use it, you may not. It's also possible that your SA failed, in which case then you're reverting back to the normal sequential execution. You did your virtual channel allocation successfully, but you didn't get the switch. So next cycle, you're going to repeat switch allocation. Okay, so that's, if you do that, you can cut the router to a best case scenario 3 cycles. Can you do more? Well, of course. Here, you're doing switch traversal even in the same cycle. This is assuming where delay is not a big problem. You allocate the switch and then you just go. In that cycle, you get it. So you can do 2-cycle routers. I mean, this is really just theoretical talking, right? You can slow down the clock speed and do everything in 1 cycle. So you have to go and balance the consequences of all these design decisions. Here, they're just sort of technique that you can possibly employ. Finally, what if I don't want to have a 2-cycle? Well, turns out you can do everything in 1 cycle. Well, but all these secondary steps that we did, SA, ST, VA, they all depend on route computation, right? So you do the trick of what can be called software pipelining. Okay, you pipeline the thing ahead of time. So what you're doing is at the node I, you are not doing node I's route computation. You're doing node I+1's route computation, which is why it's called next route compute. When you do next route compute, then this is no longer on the critical path for VA, for all these other things, okay? Because you're computing what happens on the next route. This one is already computed. It's in the header. You already knew it. It's carried. So on the very first node, you actually have to compute 2 routes. Okay, what's the first step? What's the second step? Okay, so there's some practical limitations. You see that these are, ideas that can be easily conceptualized, but they're not necessarily easily done and give you the performance benefit that a simplistic assumption of 1-cycle router can give you. But these are the things, just like a microprocessor, you can go and try them. So we talked about all these buffers. Here's again to generalize what happens. The approach that we were assuming pretty much can be sort of graded into this category, that we have virtual channels. Every virtual channel has its fixed memory, and when the data comes in, depending on the header and the information, we know which one is sending us, so it will be directed to the right VC, to the right buffer, and the packet will get stored there. Well, then if I'm not using all these VC, obviously the storage will get will not get used, will not get high utilization. So what can you do? Well, you can try to share resources. For instance, you may have all the memory buffers from one channel as one pot being shared, one pool being shared from all the VCs. Hey, you can even have the entire thing in some global memory. Just approved memory to keep everything. When something comes in, you write them somewhere. You remember the pointer to their starting, ending location, whatnot, and then you start to do all the subsequent things. And whenever you read, you go to the memory and read. And then you have the port contention issue, and you deal with that. You use multiple banks, whatever you want to do. So again, there's a lot of flexibility, design space in how you actually implement it. When we talk about the switch, we were assuming implicitly that it's a crossbar, so anybody can go to an output port. So you have input ports and you have output ports, so long as they are not in conflict with each other, you can have whatever connection. You can use a crossbar to implement this, or you can use a bus to implement this. And that requires you to have a very wide bus. Here we give you an example where the input ports have all these flits coming in. Okay, packet A have 4 flits, and I have 4 input ports, and I have a bus 4 times the bandwidth of any of these input ports. So when the data comes in, and I can say, oh, if input port wants to go somewhere, I accumulated enough data to go in one cycle, boom, there you go, that's A. And F goes in the next cycle, and so on and so forth. And once I arrive at the output port, and they become deserialized, and then they can go out of the port. Okay, so that's the timing diagram. This is how you do things. Okay, you have a one-time bandwidth coming into a deserializer, so you accumulate that into a 4 wide, and then you allocate for a bus. You arbitrate for the bus, which is a shared medium device, and then the correct output unit would get all 4 in one cycle, and then serialize it into the form that matches the output, that matches the bandwidth of the output port. So you can use that instead of a real crossbar. If you say, okay, this bus is too expensive for me to build, you can go somewhere in between. You can have 2 buses, each one having twice the bandwidth of the channel, and then you allocate those. Or, of course, you can go to the extreme, which is a crossbar. So these are all design options. In case you're doing in an actual crossbar, here's one notion or one design option, and that's called a speed up. You can have an input port speed up, you can have an output port speed up. Let's talk about input port speed up. What does that mean? Well, I have 4 output ports, so if I have a 4x4 switch crossbar, that's perfectly logical. Right? It's internally, these are the 4 input ports, 0 to 3, and I have my 4 output ports, and I can decide to connect this one, that one, this one, and this one. Right? I can do that. And at most, this switch has a throughput of 4 times the channel throughput. Okay? What if I make this taller? I have 8 input ports, like the example that we showed down here. We have 8 input ports, 4 output ports, and that's called a speed up of 2. Okay? It's not really the increase of speed, but it's just a notion, it's just a term. Why? What's the benefit? Because in such a system, at most, you will have a throughput of 4. Now that's determined by your output port. So why do you have more input port? Well, it's to give you chance of making those output port count, making them occupied, busy. Okay, here's the formula, and you can see. So suppose I have a 4x4, and assume the 4 input ports each are randomly selecting their output port. So if I look at this output port over here, what's the chance I will go empty, that nobody wants to send me anything? Well, there are 4 nodes. Okay, let's say I have k input ports, and I take a look at this particular input port. Where can he go? What's the chance of him not wanting to send me anything? Well, that's k minus 1 over k. That's the probability. Okay, that's the probability that I will not get anything from that particular node, right? Because there are k nodes, or k ports over here, and this node has equal probability, assuming going to all k nodes. Okay, that's just that input port. What about this input port here? Well, it's the same. So if I look at all of them, all different input port, I would get a result like that. Okay, this is the probability I don't get anything sent on this port. Okay, and it's the same for every other port. So the probability of occupancy is 1 minus that. 1 minus that is the chance that the port is busy, sorry. So therefore, that's utilization. So this is your utilization. And if I have input speed up, I have more possibilities to choose from. And this number is increased by s over here. So we can take a look. If I have a 4-port system, if you plug in the number, I have a 4-port unit, about 75%. That makes sense because you have 3 ports. That's not you. So any message has a 3 in 4 chance of not hitting you, and that's your probability of occupancy. And if I increase my input speed up to 2, and that goes above 90%. If I select it to 4, that's practically 100%. So I can get very busy. So that's some reason why there's the notion of input speed up. Okay, how do I decide who gets there? And that's the domain of arbitration. Oh, by the way, before that, we can also have output speed up. Now, what is the opportunity? Well, then my throughput of the switch is just 2x. Okay, even though my let's say my occupancy is not 100%, it's 80%, but I can do more. So I make sure the switch is not a bottleneck. And then if you have to match the output port, then you need to buffer this, because otherwise you may have more than what you can chew. You're biting off more than you can chew. Arbitration. And this is basically the idea. I have different requester. They all want certain resource. How do I decide who to give them the request? You can think about an arbiter being a black box with input on the left hand side. These are requests. 0 means entity 0 wants to use the resource. This in this case would be port 0. And on the right hand side would be grant. Okay? I allow input 0 to get it. So the timing diagram would be something like this. Here we're looking at 10 cycles of operation. At cycle 1, both 0 and 1 raised their request. Okay? And we decide to give it to 0 because of priority. Let's say we have fixed priority. The lower the number, the higher the priority. So 0 gets the request. Okay, that's very simple for one cycle. And because your request is granted and you have no new action, so before the end of the second cycle, you deassert your request. R1, on the other hand, did not get its request satisfied, so it persists. And therefore, it will get the chance, since now nobody else gets it. Okay. So a fixed request arbiter is rather simple. This logic over here tells you how that goes. If the request 0 is 1, then grant is 1 the next cycle. We kind of didn't draw the timing, that the sequential element of it. This is just, okay, G0 next cycle should be 1. R1 will drive G1 to be high, provided R0 is 0. So there's the inverter. If there is no request from that, then G1 is high. And if there's no request on this one or this one, then R2 can allow G2 to go on, and so on and so forth. So this is fixed right, okay? You may have a little bit of variation on the request thing, where request is a separate signal from hold, and hold basically tells you I have a request, but it's this long. It's not one cycle. I have more. Okay, so then the timing diagram is a little different. Yes, that's good. It gets the job done, but it's fixed priority. We can have starvation. We don't like that. Okay, you can have a variable arbiter, which is not that difficult. You basically have this general logic that gets repeated a lot. It basically has some sort of a token, if you wish, a grant signal from the previous one. Okay, that tells you you can issue you can be granted a request. You either have the priority yourself, that the priority is being given to you, or it's being given to somebody else, but they didn't need it, and it falls through, carried over to you. In either case, once you have the priority, this is an OR gate, you have the priority and you have the request, then you get a grant. Okay. If you don't have a request, then you simply pass on whatever priority that you were given to the next door neighbor, and if you stack them together in a couple of them, then you have a variable priority arbiter, and all you have to do is to inject a one hot variable over here. Okay, if you want this to be the high priority guy, you would go 1 0 0 0, and that's the priority. So request 1 will have priority, and you can have a different random priority vector, rotating vector, whatever you want to do. So this is, some examples of arbiter. You can do other type of arbiter, and read the textbook for detail. Allocation is a different issue altogether. Well, I shouldn't say altogether, but quite different, in that it tries to take into account, it's an allocation problem, not arbitration. Arbitration says everybody has requests and we're just granting them. Our allocation says which one we may want to adjust, who issue what request. If you imagine, why are we even discussing this? It's all because of this big switch. Okay, and we need to decide who gets it. So you can have arbiters. You can say, well, I have 5 input ports. Each one, let's say maybe there are 3 virtual channels. So I can have a local arbitration to say, okay, only one of you can use my input port to the switch, to the internal crossbar. So that's an arbitration. You can each request, and I give you some sort of priority scheme. So maybe it's rotating. You are the highest priority now. The next cycle it will be this. The next cycle that, and rotating. And once I did get arbitration, then I can further arbitrate to say, okay, there are these 5 ports. How many of them want this port? And we can bring these guys all over and arbitrate among their requests. If there is only one request, then that's it. So that's arbitration, and you can go through the switch using a series of arbitration schemes, and this is exactly how 21364 did it. Local arbitration, global arbitration. Allocation says, okay, this two-step approach may be inappropriate. Maybe here we killed a request, but that was actually a request that's good because it's going to some output port that nobody really wants, so it can actually get for free. So we shouldn't decide already who gets the input port. We should look at the global situation. So here's what you want to do. You have, for every input port, let's say input port 0, you have 3 different options. Okay, and these are what output ports you want. R00 means you want the output port 0, R01 means you want output port 1, and so on. And for each input port, we have different amount of requests indicated by the bold line. Okay, so a bold line means I want that port, and a non-bold line, a regular line, indicates I don't have that request. So if I go through two-step arbitration, this is what happens. Since only one request can use the input port, then let's say we choose 0. And here we choose also 0, x10. And since there is only one, we just get that being our request. And finally we choose, this is local arbitration. And then we have to go to global arbitration. So we come here, 2 requests, we can only grant one, maybe that's G00, which means it's this guy. And here I have 2 conflicts, then I grant one guy, which means G21. So when you look at it, you would say, well, that's bad. Okay, bad in what sense? Let's just look at this example over here. X31, it was selected and it wasn't granted. Okay, 21 was granted. Had we chosen X32, we would have gotten it because nobody wants to go to output 3. So allocation is a global look of this problem and give you one solution. Okay, and you can sort of map this to maximum bipartite graph matching problem in the mathematical way, but typically in real circuit we're talking about a real small number of these, so there are some heuristics to say, well, let's just do it. It's not guaranteed to be correct, to be optimal, but you know, it's good. It works in the common case. Here's one example. There are other examples. You can come up with your own. It's called the lonely output allocator. So what does that mean? Instead of these 2 arbitrators that we did, right? That's exactly what we had before. Now, instead of sending them the request as we did before, 1 being I have a request, 0 being I don't have a request, we send them something a bit more informative. We count how many requests there are. So to use that as an indication. So for instance, the example that we show over here, let's clean this up, R32 is going to output port 2. It's it's the only one, not in the global sense, but it's not a very hot port. So if you want to issue that, then you might get a better chance of succeeding. So that's the idea here. So what we did is we reshuffled them a little bit. So here, the first subscript indicates your source port. The second subscript indicates your desired destination port. So R02 means there is a packet that wants to go from 0 to 2. Here we reshuffle them. We take every input port's number 2 output port 2 going request, and we collect them together. here. So we put all the destination, all the requests to the same destination into one big counter. Okay, then we can see which port is more lonely. So after that, the count will be done. Output port 1 is very popular. There's 4 requests. Output port 0 and 2 each get 2. And this would therefore be sent. So if you remember the first example, we had 111 over here. Okay, we have 3 requests, 11 over here, 110, if you wish, 010, 011. Now instead of that, the ones are all replaced by frequency. Okay, so instead of 111, it's 242. And what you're doing here is you are indicating this second one, by the way, is going to a very popular port. So, choose it carefully. Therefore, we can then see from this step, pick the loneliest output that you have. And then what we do is we send out these requests. We want the 32, the 21, the 10, and the 00. Okay? These are the lonely ones. I don't have the animation. So then we go on to do arbitration. Out of these 2, we can only pick 1, but there is 1 to 1 and 1 to 3. In this case, all 3 output ports are occupied. That would be a little bit better than without this allocation scheme. Okay, so here is another allocator. Okay, this is fairly interesting. It says, well, let's do this somewhat in a distributed fashion. So the idea is we take all the requests to different port and express them as a matrix. And if one request gets selected, it must get 2 conditions, because this is how it works. I have a switch, right? What does it mean that I grant 0, 1? It's port 0 to port 1. Then the input port of 0 cannot select any other request, and the output port of 1 cannot select any other request. Okay? So in a way, if I describe them into a matrix, like what I'm doing over here, then the same row represent the same input port, the same column represent the same output port. So this matrix can only have a 1 in any row or any column. And the way we do this is we seed some tokens to different places, and we see who can grab them. If you want to go, let's say you're sitting here, you have a request. That means your input port 1, you want to go to output port 2. You want the input port 1's token and the output port 2's token. If you get both, you can go. If you don't, you can't. Okay, so how do we do this? Well, we have 3 ports, so we will get 3 pairs of tokens, and you can give these initially to whatever you want. It can be the main diagonal, the auxiliary diagonal. We're giving it to the main diagonal. And then once you have, you're circulating. If you need it, you get it. If you don't need it, don't get it. Okay, so here we're showing the request. Perhaps clean this up again. The request in highlight in the yellow node. So there's a request over here, there's a request over here. They would all want to stop the X and Y direction tokens. And the X and Y direction tokens obviously rotates in the X direction or the Y direction. So step 1, we give it to all 3, and it so happens in this case, nobody wants them. So all 6 tokens get distributed in one step. They will move to that location. And of course, this guy is happy, grabs it. This guy happy, grabs it. Those tokens are never going to circulate. And this on the other hand, is not grabbed by anybody, and it will just keep on being circulated, and we will get to nowhere. And indeed, for this example, we don't have a solution because the only request that we can allow would be this one, and we don't have a request over here. So that's one example, and this is how the circuit goes. The idea is very similar to earlier arbiters. If you don't have something to stop it, you're passing the grant, you're passing the out to either X or out. If you have the priority coming into you directly, given to you, or being passed on by your upstream neighbor. So that's another allocator. And that's about it. There are all these little things in a router that you need to do system-wide. You may have to decide on the design based on some performance analysis. There are all kinds of pitfalls if you do a simulation-based analysis, and it's all described in detail in chapter 23. Wonderful, but a lot of basically checklists wouldn't be something I recommend you to memorize now, but more when you're doing the design, take a peek. There's some very commonly make mistake. For instance, you're simulating this thing and you forgot to warm up, meaning you start from cycle zero, and you start to send packets, and you want to measure the latency and such. Well, at cycle zero, the entire network is cold. Okay, all the queues are empty. That's not reflective of what's happening. So what you need to do is to start to inject packet following the traffic pattern that you care about. Okay, you have to warm up for a certain amount of time before you start to say, from now on, I'm going to track the subsequent packet that enter the network and measure their latencies. So there are a whole bunch of measurement pitfalls. I would not go through them. There's not a whole lot that requires explanation. Just go read the textbook. It's the best way to get familiar with them. I mentioned some detail over here that can help you with this section. So that's a very short summary of the interconnect, the components you need to route them, what topology you have, and then what about flow control in the dynamic situation. You need to worry about deadlocks, and in the end, once you have all these policies set up, it does prevent deadlock. How do you actually fabricate them? Well, you need to get down to the business of designing the microarchitecture. So it covers everything, and that's about it. There is just one more topic that's particularly relevant to interconnect, and we'll cover that next. And that's a very quick, oversimplified look at queuing theory.